Okay, so welcome to the next lecture. So in this lecture we shall introduce the notion of metric spaces. So metric spaces provides perhaps the most important class of topological spaces. So after we introduce metric spaces, we will also see, we have talked about open subsets, closed subsets, continuous maps. We will give descriptions of these in terms of the metric. Okay, so let us begin by recalling the definition of a metric space. So we recall the definition. Of a metric space. So definition. Let X be a set and let D from X cross X to the real numbers which are greater than or equal to 0 be a function, be a map which satisfies the following three conditions: d of x comma y is equal to 0 if and only if x is equal to y, d of x comma y is equal to d of y comma x, and d of x comma z is less than or equal to d of x comma y plus d of y comma z for all x comma y comma z in x. Right? This is for all x comma y in x. Okay, so this is called the triangle inequality. Right? So the D is for distance, yeah, and we know that if we have a triangle, right? So this is x, this is z, and this is y. Then the distance between x and z is less than or equal to the distance between x and y and z. Yeah. So if these three properties are satisfied, then we say that then the pair x comma d is called a metric space. Right? And the map D is called the metric on x, or the distance function. So we just need any function D which satisfies these three conditions, right? So given any set X, there could be lots of metrics on X. Okay, but the most common example of a metric space we encounter is Rn with the Euclidean metric, right? So that is, if we have two vectors in Rn, right? So x is x1 up to xn, and similarly y is y1 up to yn. right? So then d of x comma y is defined to be the square root of the sum of squares of the difference of xi and yi. Okay, so let us check that this defines a metric. So let us check. That this defines a metric, right? So note that the first two conditions are trivial to check, right? The only non-trivial condition is the triangle inequality, so which we will prove now. Yeah. So proposition. So this d of x comma y, we shall write this as norm of x minus y, the 2 norm. Yeah. So we will use this notation instead of writing d of x comma y. Okay. So what we need to prove is that with this, in this notation, that the norm of x minus y is less than or equal to or alternatively, I mean, we can define okay, let me just so if for a vector x in Rn, we define the 2 norm of x as summation xi square and square root of this. Yeah. So then clearly, I don't need to write this as a definition. So then clearly d of x comma y is equal to the 2 norm of x minus y, right? And to check that this defines a metric, we need the following proposition. It's precisely the following proposition. The norm of x minus y is less than or equal to for all z in R. Right? So let us prove this. So it is enough to check that and this left us an easy exercise, that it's enough to check this. Right? For all. Right? So in order to do this, so consider the map, right? This inner product defined as xi by I. Okay, so we first claim that this absolute value of this quantity is less than or equal to into norm by 2. So let us first prove this claim, and to see this, so let us define w to be equal to y minus tx, where t is a real number, right? And now let us compute. So this inner product of w with w, right? And this is equal to this is bilinear, right? This is bilinear in both. So what that means is, if we fix x, that is if we fix x, then x comma lambda y1 plus y2 is equal to, or if we fix x, then it is linear in y. Right? And similarly, if we fix y, then linear in x. Right? So using the bilinearity, we get that this is equal to minus 2t into x comma y. Right? And it's also symmetric, bilinear and plus symmetric. Right? Because clearly for symmetry, x comma y is clearly equal to y comma x. So using the fact that this is bilinear and symmetric, we get this, but this is precisely equal to t square, yeah, minus 2t. Yeah. So for a fixed x and y, we view this as a quadratic in t, right? There is a degree 2 polynomial in t, and as it only takes positive values greater than or equal to 0, it follows that the discriminant is less than or equal to 0. It follows that the discriminant is less than or equal to 0, right? But what is a discriminant? So the discriminant is 4 square is less than or equal to 4 into which proves our claim, right? Right, this is the claim which we want to prove. Right, this is the claim which we want. So using this claim, we will now prove the proposition. So note that so we have norm x minus y whole square is equal to this is equal to and this is less than or equal to yeah. So over here we have used the claim, So, oh sorry, we have not used the claim yet. This is less, we are just taking absolute value. This is less than equal to. Now here we have used the claim. Whole square, right? So this implies that and note that the norm of y is same as norm of minus y, so therefore we can just replace y by minus y and we get okay. So this shows that this Rn comma D is a metric space, right? So this proves triangle inequality holds, and therefore this is a metric space. Okay. So this is the main example of metric space. Okay. So now, given a metric space, how can we use the metric to define a topology on it? So let us see that. So given a metric space X, we can use the metric to define a topology on X. Yeah. So for that, for X and X and an epsilon positive, define the open ball of radius epsilon around X as follows. Okay. So B epsilon X is defined to be those y in X such that the distance of X from y is strictly less than epsilon. Okay. And we consider the collection. There is something which we are familiar with. B contained in the power set of X, defined as, so B is the collection of all these open balls around various points of X. X is in X and epsilon is positive. Okay. So it is easily checked that that B satisfies the two conditions for being a basis. Right? So thus B defines a topology tau on X which has B as basis. Right? And so therefore, in other words, so thus a subset U contained in X is open in this topology if and only if it satisfies the following property. for every u in x, or sorry, for every x in u, there exists an epsilon positive such that this open ball of radius epsilon around x is completely contained inside u. So this is very similar to the examples that we saw in the beginning of the course, that is Rn. So yeah, so if we have our topological space X over here, so a set is open if and only if given any point X, we can find a ball of radius epsilon around X which is completely contained inside U. Yeah? So the epsilon of course depends on X. Yeah? So it is trivial to check, and this is left as an exercise. That the topology defined on R, Rn, using the Euclidean metric is the standard topology. Okay, and this check is left as an exercise. Okay, so now we want to understand what it means to be in the closure in a metric space. Yeah, so in terms of the metric. So definition. Let X be a metric space and let Xn for n greater than or equal to 1 be a collection of points of X. Okay, so we say Xn converges to X if for every epsilon positive there is an n sufficiently large such that for all, let us say, n naught, and this n naught depends on epsilon, such that for all n greater than or equal to n naught, the xn's are contained in the epsilon ball around X. Okay, so this xn, so I should write xn converges to, we say xn converges to X, right, and it's often written as xn converges to X. Okay, so roughly if we have X and X is here and we have a sequence of xn's, so we want this sequence to get closer and closer to X as our n tends to infinity, right. So, or precisely what we want is, yeah, no matter how small we take epsilon, when we take the epsilon ball around X, after finitely many n's, all the xn should be in that epsilon ball. Okay, so let us prove this lemma. Let X be a metric space right, and let A contained in X be a subset. Then X is in A closure if and only if there is a sequence xn converging to X and xn belongs to A. So X is in the closure of A if and only if there is a sequence in A which converges to X. Right. So let's take a simple example. So if we take, let's say, this region, right. So then given any point on the boundary, we can find a sequence inside this red region. This region x square plus y square is strictly less than 1, right, which converges to this point on the boundary. Yeah. But if we take some point outside this boundary, then we won't be able to find a sequence. Yeah. So yeah, then we can find a small neighborhood around this point outside which does not meet this set A. Yeah. So therefore we won't, no matter which sequence we take inside A, yeah, it will not satisfy the definition of converging to X. If we take a point outside this circle, x square plus y square is equal to 1. Yeah. So that's a small example of what is happening. So let's see a proof. So let us assume that, suppose X belongs to A closure, right. So let's say X is over here, right. So then by the definition of closure, every open subset U containing X meets A, right. So take U to be B1 upon n X. So we take UN to be this collection, right, and we choose, so each UN it meets A because X is in the closure, right. So choose any xn in B1 upon n. This epsilon, this 1 upon n neighborhood of X. So we are taking this, we are taking smaller and smaller neighborhoods, right, and inside each neighborhood we are choosing, each of these neighborhoods it meets this red region, and we choose one point in that intersection A. Yeah. So then we claim that xn converge to X, right. So to prove this, what do we need to show? So we need to show that given any epsilon positive, there exists some n naught very large, so that such that for n greater than or equal to n naught, we have xn belongs to b epsilon x, right. So let us show this. So note that first choose, so we can choose n naught sufficiently large so that 1 upon n naught is strictly less than epsilon, right. So then we claim that n naught we have b 1 upon n x is obviously contained in b 1 upon n naught x, which is contained in b epsilon x, right. And moreover, this these balls, these are nested, and so on, right. So from this and xn is here, xn plus 1 is here, and so on, right. So all this is contained in B1. Right. So therefore this shows that, so this implies for all n greater than or equal to n naught, xn belongs to b epsilon x, which implies that xn converges to x. Okay. So conversely, suppose, so in the first part of the proof we showed that if x is an A closure, then we can find a sequence of xn's in A so that xn's converge to x. Yeah. So and conversely, so suppose xn's is a sequence in A such that xn's converge to x, then we need to show that x is an A closure, right. So once again we will use a definition. So let U containing x be an open subset, right. So by the definition of the topology on x, which is given by the metric, right. So then there exists an epsilon positive such that b epsilon x is completely contained inside U. So U is some set, open set which contains, and let's say x is here. So we can find an epsilon such that b epsilon x is completely contained inside U, right. And so as xn converge to x, so this implies that for all n greater, there exists n naught such that for all n greater than or equal to n naught, xn belong to b epsilon x, right. So this implies that xn belongs to b epsilon x intersected A, which is contained in U intersection A, right. So thus U intersection A is non-empty, right. So thus x belongs to A closure. Okay. So we have given a nice, so in case of metric spaces we have given a nice and intuitive criterion for what it means for a point to be in the closure of a set, right. So right. So once again we return to our earlier example. So the closure of this set, we are taking this open region, A is equal to x square plus y square strictly less than 1, right. So the closure of this is exactly the set A closure is equal to x square plus y square is less than or equal to 1. Okay. So we will end this lecture here.